Alright, hell yeah. So what we have going on is a college student's problem. It's a statics problem, and we're going to do it. So I'm going to try to just do it start to finish. I've already done this one about 3 or 4 times, and I'd like to make a few videos on it. But this problem is kind of tricky because it involves friction. And I think the simplest demonstration of friction is some sort of block that has a mass and it's resting on a table, and we're going to say, hey, there's a friction on this table. You know what I mean? So you could make it all rugged and rough. And so what we're going to do is we're going to pull on this with a force, and then the question is, what's the force at what value, you know what I mean, in newtons, let's say, do I have to pull, let's say with a string on this mass, to get this thing to just to start to move? And so we know that this box or whatever chunk of mass has a weight to it, and that weight is going to be its mass times gravity, because we're going to assume that we're going to do this experiment on Earth. And I've told myself, anytime that we're going to do the weight is equal to mg, I'm at least going to show you where this comes from. So weight is equal to the force of gravity. The force of gravity, the equation for that is the gravitational constant. The mass of whatever, you know what I mean, and times the mass of the Earth divided by the radius. And this is the radius from the center of the Earth to the center of this box. But it doesn't matter whether you're on top of Everest or the sea level. Well, it kind of does. It'll change by just a very small amount. Your weight will change about 8 ounces. But basically, it's just the radius of the Earth squared. These three things don't change. This is a constant, mass of the Earth, radius of the Earth, and so you get mg. G is just designated as this. And so this student's going to use 9.81. You could use 10, you know what I mean, and just kind of go through and get a halfway rough answer. It'd just be just fine. Hell yeah. Alright, so that was a little tangent. But once we know the weight, we know this relationship, you've probably heard it, that a rough surface, and it has to do with two things. You know, whatever this material is made out of, maybe it's wood, and maybe this surface is metal, and so like steel. And so then you get this coefficient of static friction. Let's just say it's 0.3. They usually are between like 0.3 and 0.5. Now I did this problem 100% wrong my first go through. I didn't even use some of the parameters. I was just kind of in a who cares method. I got the right, so here's the right answers. In my first go around, I got mu is equal to 2. And then the student's like, hey, doesn't that have to be less than 1? And I was thinking, I was like, nah, I don't think so, but I was just going to agree with them. I was just like, yeah, it sounds hella wrong, and I did. I knew I got the wrong answer, but hell no. Friction can be greater than 1. It's just not, you know, for whatever reason. But it can be, because what's happening at this molecular level is literally this rough surface. You could think of it as Velcro, you know what I mean? If you have a mass, and, well, let's just think of this rough surface as kind of Velcro, where you have, let's say, these curly nylon little grippers, and they're going to grip into the surface, you know, of that block. You know what I mean? So this is the surface of that block. And when we move this block, that nylon is going to stretch out until it can no longer hold, you know what I mean, that eyelet. And that eyelet's going to slip off. But this process is constantly repeating itself, you know, hundreds, thousands, tens of thousands, maybe million times over. Well, probably even a higher level than that, at a molecular level. So this is what's providing that linear, you know, consistency. And even if this starts to move, you know, your coefficient of kinetic friction is still just a constant value, because that surface is constantly gripping, constantly leveraging, and constantly breaking, and then constantly gripping again. Once this eyelet lets go, it's going to pick up another one that's perfectly curly-cued, and then that's going to stretch out. So that's just kind of my intuition when it comes to kind of what's going on at the molecular level. You do have jagged pieces, you know what I mean, at this level you do have this, and because these jagged pieces can be very small molecularly, you are going to get probably distortion of these lips as they break apart and then catch a new surface. And so that process happens repeatedly. But where this coefficient of static friction comes from is any two surfaces that you're just resting against one another. So, I mean, if you rest two blocks that are attached to Velcro, well, then this process of, this doesn't really apply because you're kind of changing the game. What we have is, like, if you have just wood and metal, what happens if you just have a very, very light piece of wood, just on a metal surface, it's, let's say you just have let's give this some value. So I'm going to say this is 1 kilogram, and we're going to say G is 10. And so this thing weighs 10 newtons. Cool. And we're going to say the coefficient of friction is 0.5. Just up it a little bit. And so what's going to happen is it's going to take 5 newtons to get this thing to move. So that's the deal there. That's that linear relationship between what's going on at the molecular level, kind of gripping, stretching, and then regripping. But when it comes to just that's kind of this scenario I like to visualize for kinetic friction because you're constantly doing that as this thing's moving. Now, static friction, you're just going from like, hey, the second you rest this wooden block on this metal surface, you still have, this connection, little eyelets and like Velcro straps, and the force to release these, the first ones, we're going to stretch them all out, and then at some point they're going to release. And that's going to be the force to release that block and send it from a static position into motion. And so I still think this is a pretty decent, a lot of textbooks, they'll show jagged surfaces, and you still got molecules chilling, and you got molecules interacting, and you for sure got molecules, bending and releasing. Well, in the case of static friction, you have molecules that are bending, yielding, and then at some point, you have a release, and that's going to be the force required to get that thing to move. All right, but hell yeah. So the take home on this was if we chose 1 kilogram, it's going to be 10 newtons. Static friction is 0.5. So the force required to overcome the friction, that force is going to be whatever the weight is. And we're going to do mu times, and typically it gets written as the normal force. You know what I mean? Because if this block was a free body diagram, you know what I mean? This is where I kind of say it's floating in outer space. And we still know that we have a force due to that. So we have that mg. And because on Earth, when we run this experiment, we know that this block's not moving, like down or up. That's kind of the direction we're kind of curious about, because we have a mass and we've just identified that we have a force on it due to the Earth underneath it. So from our free body diagram, it would appear that this thing's moving this way. We go back to Earth and observe that in this experiment of just resting a block on a wooden block on a metal table, it's not moving. And so there must be an equal and opposite force, and we call that the normal force to balance that, and that's going to be equal to mg. And then so the force required to actually put this thing into motion, this direction, has to overcome the friction force. And this friction force is going to be mu times the normal force. And think of this as a max, because you can obviously, if this thing weighs 1 kilogram, and the normal force is 10 newtons, we're going to have 0.5 times 10. And that's going to be a force of friction to overcome of 5 newtons. Let's say I just put a force of 3 newtons. Is anything going to happen? Hell no. 4 newtons? No. 5 newtons? That's going to be right at the point of impending, like movement. So that is also the thing that I always have to make sure I pay attention to when it comes to force of friction. This force of friction just balances whatever you're throwing at from a minimum of 0 to a maximum, and it can function in both directions. So it just opposes the direction you're pulling. So if this is the net pull in this direction, the force of friction is going to be that way. If you decided to pull this way with a force net of 4 newtons, hell yeah, the force of friction would balance of 4 newtons. And just know that the max value can only be 5 newtons for this little experiment that, we're trying to set up the simplest problem before we kind of tackle something more complex. Alright, hitting hell yeah. And from this we have our equation. We have our equation that says the force that I need to pull, the force, to pull, and move. So, and move is going to be, is going to be proportional to that force max, that friction force max. You know what I mean? So that's kind of what, and then so let's just go back to the general equation. We said that the force that we're pulling, this I might have said it wrong. That's where it's just I always go back to like, hey, the frictional force can have the max it can be is the normal force. So yeah, so let's say force of friction max is the coefficient of static friction times the normal force on that mass. So when you take that mass and rest it on a surface, the normal force on that, and the normal force also could be at an angle, so you could, for sure you could take this and make it an inclined plane problem, and it would be the normal direction, where, like this, all the weight is on that perpendicular surface. If you moved it to a 60-degree angle, that's the angle that only half of the weight is actually normal into that direction due to a 60-degree angle. And so, but anyway, so we have a flat surface, and really we're not even worried. This block ain't moving. We're actually going to rip this post out. And the crazy thing is we're going to have to rip it out at both locations. And so our problem is going to be way different than, it's going to be different than just a resting mass on a surface. So, and we're going to explore that. But hell yeah, so here's going to be our equation. Is that the max frictional force is going to be the coefficient of static friction times the normal force of that mass on that surface. Alright, hell yeah. And it seems like, even to me, something's missing here, because let's do our free body diagram again, and let's put all the things that we want. I'm going to take this mass, and I'm going to put a force on it. Now, this force is what I want to figure out what that force is. Okay? And we said if the force is in this direction, we're going to have a frictional force that's going to oppose. That's going to be the force of friction. And I always write this subscript max because it shows you that, hey, you need to double check this. Because the problem that we're solving is what's the force to get this to move. Sometimes you have a coefficient of friction and you just have a problem that has a force, and then you got to double check whether this number is so large that it is going to move, or it's just small enough where the force of friction is going to do its job and just hold it stationary. Alright, hell yeah. So this is going to be the driving force. And I'm going to call it P from now on. because that's what we have in the problem. So we're going to apply a force P on this mass, and we want it to move, but we want to just apply just the right amount of force so it actually moves. We know that this has a mass, so its weight is its mass times that gravitational constant, which we just call gravity, mass times gravity. I think that's the fact that people stop using, this is Newton's law of gravitation. And I even messed it up. This is radius squared. Apologize about that. And since I messed that up, we're gonna go over these. Because you can memorize these pretty easily. This is just 6 times 10, and if you don't know this one, just move on. This is mass, and this is in the mass of the Earth. Well, we're just these three numbers. It's got to be 10. You know what I mean? So that's what you're shooting for. So you're like, oh, wait, these three numbers got to be 10? So you can figure it out on the fly. This is going to be 6 times 10. And you got to remember at least some of these. So this is 24. You know what I mean? And this is in kilograms. And then the distance, the radius of the Earth, just know that it's 6 million meters. But that's going to be 6 times 10 to the 6. And then just think, I don't know, just a lot of sixes, like the devil. Science is the devil to Christians, anyway. And hell yeah, we're going to square this. And so because we have this exponential and we're squaring it, we're going to have a 6 times 6, and then we're going to have this 10 to the 6, that's going to be 10 to the 12. Cool. So this is going to be a negative 11. So bring it downstairs, that's going to be a 10 to the 11. And you can see downstairs we're going to have 10 to the 23. That's going to balance that 10 to the 24. We're going to have a resultant of 10 to the 1, 10. All the 6s. These two 6s cancel those two 6s. So, hell yeah. Anytime you're using mg, friggin' A, go back to Newton's law of gravitation. And just so you for sure know where that comes from. And this, I was just surprised that you can just memorize this from a silly little axiom that there's a hell of a lot of 6s going on. And even here, 6 squared, it's 6 times 6, and that cancels both those 6s. You know what I mean? And if you want to get accurate, we're just going to move on. All right, yeah, this is plenty accurate. This is the only one that's like 6.37. This is 5.98. And this is, what is this? And I think this literally is the devil. It's 6.6, but 7. But 6.66. 666 times 10 to the negative 11. Yep. So anyway, so it's just always good to memorize things from a who cares perspective. Like, hey, there's a bunch of 6s, cancel them, and then just your 10s. And then start to memorize your decimals to 3 decimal places. 5 times 5.98. You know what I mean? 6.37. And I think I have that one right. And 666. You know what I mean? And just 6.67 times 10 to the 11. Cool. Awesome. Let's move on. Alright, we did that because this weight is the mass times gravity. You know what I mean? Such a dumb thing to say. But anyway, mass times gravity. And, cool, that's the weight. And then, therefore, the normal force to balance. The forces in the y. We have it from a Newton perspective, this free body diagram. And I've come up with a couple ways to think about this. Is that you can always take a problem, and I like to just put it in outer space. That's literally the definition of a free body diagram, where the mass that you're analyzing is totally isolated in its own universe, and then you are applying the forces, the known forces that we know kind of back on Earth on this experiment. So on Earth on this experiment, we know this thing is made out of mass, and we know that the Earth is trying to put a force down. So we can take our block in outer space and we can put our own little force. I've thought you could just make a little rocket, a little lightweight rocket that blasts it in that direction. And then you got to go back to Earth and be like, hey, this thing's not moving. So our experiment in outer space also can't move in this direction. So we have to have an equal force to balance that. And this is going to be our normal force. And so very simply, forces in the y direction have to equal 0. This is going to be a downward force, so we have negative mg. This is going to be an upward force plus n. Those have to equal 0. Get this to the other side. or just by observation, this normal force has to equal the weight. And so that's what we have. Now I'm going to write the force of friction mass is going to be this equation, the coefficient of static friction times the normal force. Cool. So we know what the normal force is. And so let's do sum of the forces in the x direction. Same thing. I'm going to pull on this, and the frictional force is going to resist. Now I did say that I want to pull on this until it moves, but there's going to be a split second right before it moves that the frictional force is maxed out, and my pulling force is at a critical value, or that's at the point. That's going to be the force to start movement. But this right before, like the moment right before movement, we still have no movement, and you are technically, like, let's say it takes 10 newtons to move this thing. Let's apply 9.999 newtons. So therefore it ain't going to move, right? It takes 10 newtons to move it, you know what I mean, from that perspective. So that's what we're going to do. We're going to apply that many newtons, and then we're going to see what's happening. Well, yeah, and it's going to be balanced. So, all right, so let's do our equation. This force is going to be, let's say, just in the positive direction. Our coordinate system is positive x, positive y. So we have this plus p, and then we have minus mu Sn is equal to 0. And so we can rewrite this as p minus the coefficient of static friction, which is mu s. And then the normal force we just said was mg from here, so that's going to be mu s mg is equal to 0. Get that to the other side, which is just p is equal to mu s mg. And then let's solve for mu s. So the coefficient of static friction, well, I forget what the hell we're even doing with this problem. What do we want to answer for this problem? We said this was 0.5, and we said the block weighed 1 kilogram. So we want to know this force P. So this is our equation. So P is equal to 0.5 times 1 kilogram times 9.8. And we're just going to do 10. 10 is gravity. 10 meters per second squared. So 10 times 0.5 is 5, and we get Newton. You know what I mean? Mass times gravity is newtons, so this becomes 10 newtons. 10 newtons, whatever. And then times 0.5. So the force that we need to pull is 5 newtons. All right, hell yeah. So hopefully, I mean, we're just trying to do the simplest thing. Sorry for getting a little bit heady on that. But yeah, with a coefficient of static friction of 0.5, our normal force is 10 newtons. It just means that we need to pull a force of 5 newtons. But again, this number could be hella extreme if you just have some sort of bizarre material where you put the two materials together. And, it still has to behave linearly. If this thing is to, if your materials are to behave where you can give it a value of a coefficient of static friction, it for sure has to obey this property that you put a little bit of weight on it, then, I could have a wooden block and then this steel table, and then I can just add more blocks to it or just add more weight. And if I double the weight, it's going to double the force to make it move. You know what I mean? And so that is kind of the linear relationship. I increase the weight by 4. This number that requires me to pull it to get it to move also increases by a factor of 4. So sure, there might be materials that can have a coefficient of static friction greater than 1, but I think you'd be probably hard-pressed to find one that still behaves linearly, you know what I mean, which is pretty much the definition of using this. Anytime someone marks a material and says this has a coefficient of static friction, that for sure means like, don't quote me on that, but it's assuming that that thing is going to be linear. So the less weight I apply, if I apply almost no weight, it's going to take almost no force to get that to move. And then if I apply some weight, it's going to take that force, double the weight, it's going to take 2 times that force. Triple the weight, 3 times that force. So we have a linear relationship there. Alright, sweet. Alright, hell yeah. So now this is where I think you need to get creative. And so what we're going to do is, because our problem is a little bit different, and we might as well just grab a fresh sheet. So our problem is, like, if this is our mass, it's sandwiched. And so, like, let's go back to, like, let's say I have this. Let's say I for sure have some sort of ceiling of some sort, and it's hella rigid, you know, concrete ceiling. And I'm going to have a couple rollers. And what do I want? I'm going to have a bar that attaches these. And then I'm going to put some fairly stiff springs. Cool. And I'm going to put this, and then I'm going to attach a plate. Or a chunk of wood. This is going to be wood. Okay, hell yeah. And then this is going to rest on a steel table. So we have, you know, a steel surface. So this is going to be steel. And therefore, hey, we have our relationship between two materials, and we probably have a coefficient of static friction. We're just going to say it's 0.5 again. And we're going to, you know, and for this demo, just assume that these rollers and this plate are really close together. And so when we pull on it with a force, it's really, you know, let's just say it's approaching the fact that it has negligible thickness. And so still there's the ceiling. Cool, and then here's the table. So I think that is a good representation of kind of what I want to show. Alright, hell yeah. So what we're going to do is we're going to apply a force on this plate, this wooden plate, whatever you call it, and so here we're going to say this wood has negligible weight, so its mass is just really small. Cool. And the weight of all this stuff is just really small as well. But it's the springs, and these are very frictionless. Alright, hell yeah. And so these rollers are totally frictionless. You know what I mean? So you can see that there's no friction up there. It's just perfectly slick. And that's the other thing that's very difficult to, like, yeah, it's crazy to visualize. So let's say, you know, everyone loves the hydraulic press channel. And let's say you have a hydraulic press, and then you have the table underneath it. And you take this, and then here's where you're gonna, you know, put something, and then you're gonna take a chunk of steel, you know, just over that area that you would press, and you're going to, you know, push this down with 10,000 pounds, you know, whatever, 20 tons, of force on this chunk of metal. And you're going to try to, you know, and we're going to do this experiment on Earth. Well, in a second here, we're going to modify the experiment. It'd take a lot of force to rip that thing out after this thing is totally clamped down, crushing the hydraulic press. You know, the hydraulic press crushing in between this chunk of metal. But now, let's say you could flip a switch and turn off friction. And I think this is, because every simple problem in physics is just like, hey, neglect friction here, And, hey, you got a little bearing, maybe a ball bearing right there. I can understand that, neglect friction. But it's really crazy when you can just say, so we're going to neglect friction. And if there is zero friction, so we're just going to go into an alternate universe where there's zero friction, and we're going to use this hydraulic press and crush this chunk of steel, and we're going to try to pull it out. And guess what? The force required to pull that out is 0 newtons. If you start to put any force, you put 1 newton on that thing's just going to start to move out of there. It'll be perfectly frictionless, and it'll be perfectly slippery. And so that is very difficult, especially when you have something under compression. That's why I'm just showing you, like right here, we're going to have to say this surface is frictionless. But you know what I mean? You throw some wheels and some bearings, you're like, okay, I get that. I didn't need the 5-minute tangent of pretending or just imagining a frictionless universe. But it's kind of a fascinating thing. If you do neglect friction, that means in this scenario, any sort of force on that metal is going to get that to move. Let's move on. Alright, so why we're doing this is totally analogous to just a chunk of mass and a big earth underneath. So the earth is applying a force, which we call weight, which is mg. And it's pushing this block into this surface. This is wood, this is steel. And if I want to pull on it this way, I need to overcome the force of friction, which is has a max of mu s times n. Force of friction. And am I the only one that just puts a max on this? I mean, because if you don't, then the force of friction will always balance. If the net force in a particular, like x direction, this is the x direction, whether it's that way or this way, if the net force is less, so if F is less than mu Sn, then we have no movement. I guess that's kind of the definition of checking for equilibrium. If this force is greater than mu Sn, well, hell yeah, we got a dynamics problem. It started to move. So those are the two scenarios. But I just wanted to show, and I was pretty clever to come up with a couple scenarios, and we're going to do the next one that's going to show what's kind of happening here, because we have a block that's sandwiched between two rough surfaces. So this surface is rough. This surface is rough. You know what I mean? The material above it is rough. And so we have two rough surfaces. And, you know what I mean? And so, obviously, this could be any material, this could be any material, this could be a third material. And from the books, we're going to have a coefficient of static friction at those points. This is going to be mu s at point B. This is mu s at the contact point of point C. But this value, we're just going to solve for that value in our problem. You know what I mean? So we don't need to know what materials are. We're just going to solve for this value. All right, hell yeah. So in this situation, this chunk, if we do a free body diagram on that chunk of wood, we're going to have a force due to the spring. So we're going to have a spring force, and we're going to have a normal force that's basically equal to that spring force. This spring force is synonymous with weight. You know what I mean? I'll just say is like whatever for equal. And that's not the symbol. But anyway, and I'm going to try to pull on it with a force P, and we're going to have, because this is the friction surface, we're going to have a force of friction I'm just going to do max is mu s times the normal force, which is mu s times the force of the, the spring force. And then our P to move it is, let's do sum of the forces in the x direction, is 0. And so we're going to have a positive P minus this force of friction max. And at the force of friction, if this value is the force of friction max, that is, you apply any extra little force at P, it's going to move. So that's why we're using that value. These are going to equal 0. And so we have P minus mu Sn is equal to 0. We could also write it as P minus mu S force of in the spring. That's the same thing as the weight. The weight is equal to 0. Rearrange, and so we have the force P is mu S force in the spring, which is completely synonymous with what we we saw for before, which was the force required to get this thing to move was mu S times the weight. Alright, so hell yeah. So now I'm going to do one more scenario to kind of show how we can sandwich things, but then have two different values at these points. Because that's the tricky thing about this problem for visualizing, is that we're going to have two different, this point's going to have a lot of weight because we have this big mass on it. We're actually applying a little bit of an upward force, so this might have less weight. Well, it depends, because this post also has a little bit of weight, maybe a little m. But we do have a component upwards of this. So if this component Py is bigger than the weight here, little mg, this is mg for the big weight, then we're actually kind of lifting up on this point, and it's going to have less than the weight that would be right there. Okay, so let's do a scenario where we can kind of draw that. So here's my scenario: is I'm going to have a like a steel bar, let's say, and I'm going to have it on rollers. These rollers are fixed into the wall, so that's like fixed rollers. They still are able to spin. Alright, so from this point I can apply a force P. We are going to have our two chunks of wood, let's say, one top and bottom. So this is like that wood, and they're going to be resting against a steel surface, top and bottom. And let's just kind of flesh this out. So we actually have, let's say this is just all concrete, so everything's hella rigid. But then on this surface, we've boxed it in with some steel. So, and it just shows you that, with the force of friction, you're interested in the materials. We got wood on steel. And so I think that's very helpful to be like, hey, I could look that up in a book and I could get the coefficient of static friction. And again, at the molecular level, that wood is doing something like that. The steel is maybe doing something like this. And you're able to apply a force before those, those points dynamically separate. All right, hell yeah. So what we're gonna do is, and you know what? We're going to say we're looking down on this. I think that's a very important thing, especially with the free body diagram. I do want to take one step back, because we said we had this, we have a weight on a mass on a table. And if I do a free body diagram, I said I could picture this in outer space just floating, and I could put the masses in this direction. The other thing that you can do, and I think this would be kind of interesting, is pretend your free body diagram, so this is the vertical direction with the Earth underneath. Take your free body diagram and just throw it horizontal on a air hockey table. So here's the air hockey table, all the holes. And I'm still going to take, this block has 3 dimensions. But I'm going to take that three-dimensional block and then just put it on this air hockey table. This is still the front face. And I'm going to blast this air hockey table so hard that it's hovering. You know what I mean? So it's just kind of floating loosely around. And then what I'm going to do is I'm going to attach a string with a pulley and then a soup can hanging down towards the ground. And that's going to apply a force. Like, that's literally going to put a tension in the string, and that's going to simulate the weight of that in that direction. And so I just think this is very useful to think of free body diagrams, because you're totally isolating that mass, and it is like it is just floating in its own universe, and then you are applying the forces. And you're doing so in a way that the Earth is doing. The Earth is applying a force, downward, and then the table is applying the upward force. And so the table would be the other string going this direction with the same soup can. You know what I mean? And then so that would be balanced in that direction. Yeah, because under this, we have to do a few things. If I do put a steel-like surface, like that's perpendicular to this air hockey table, cool. There's no weight on it, so I could just, easily pull it in that direction. It would act like this would be frictionless. And so to actually apply weight, I would probably have to build some sort of wall, rigidly attach it to the air hockey table, and then put rollers. Put something like that, a little track, and then put those springs on there. Now, if I did that, and these springs had a spring force, where the spring force was equal to, the experiment of the weight, then I think, so this is very useful. Like, the Earth is doing an experiment on that mass, and you can take that mass somewhere else and run the same exact experiment. So, on an air hockey table, in this little contraption with those springs. So that's I don't want this thing vertical because I don't want the implication, and I just hate saying mass is negligible, because if this thing is kind of still mass will be negligible. I don't want it to fall that way either. But anyway, so if we're looking down upon this, I'm gonna do a scenario where the springs right here are pretty lightweight. So we have lightweight springs, and there might be 4 of them. We got thickness here. So we probably have 4 springs holding up a square chunk of wood, and those are going to be on rollers. So we have 4 sets of rollers, so if all of these are plates like that, looking with the side view, or just kind of at a 3-dimensional view. Alright, sweet. But over here we're going to have hella thick springs. And those are, so hell yeah. So we have hella thick springs. But see how I fix these rollers? So this spring is pushing into, for sure, these rollers. And we can ignore the free body diagrams on those. We just want an intuition that, hell yeah, these springs are hella crushing this piece of wood into this steel. Where these springs are just lightly pushing this wood into the steel. And these two sides have nothing to do with each other, okay, from that regard. Like, this spring's very light, this spring's very heavy. The heaviness ends at those 2 rollers. The lightness of these 2 springs end at those 2 rollers. Cool. All right, hell yeah. And so these springs are gonna cause like the same sensation of weight. I'm just gonna say Fs, and then over here is just Fs prime, just less. And so we're gonna say Fs prime is considerably less than Fs. Well, or just half or whatever. Who cares? All right. So, but now the question is, what's the force required to pull this system? Because that is synonymous with this. You know what I mean? So that's kind of like the take-home point, is that this problem, to make it hella simple, I think you should. So let's go to this. It would be visually simpler to put a square block underneath here on a ground surface. So you have your pivot point here, and let's just pull with a force P, and we're going to say I'm going to put a same mass above it. This has mass and this has mass. So now we have just made a simpler problem, and this is what you always want to do. You know what I mean? Like cool, yeah. And so what we're going to find is that we have a weight here. So we're just going to say that's W. And we have another weight there, W. So the normal force on this surface is 2 times W. The normal force on that surface, just kind of by easy inspection or whatever, is just W. So there you go. And I guess the question asks, what's the force required? Well, no. Yeah, it says what's our question says I want to pull with a given force, 300 newtons. We're just going to say 1,000 newtons. You know what I mean? Our problem says pull with 300 newtons. We're just going to use kind of round numbers. So I'm just going to pull with 1,000 newtons. And what it says is, what is the coefficient of friction on this surface, this prime surface, and what's the coefficient of friction on this surface? Like if you get to choose the materials, the experiment is like, hey, I want to pull 1,000 newtons, and I want these two surfaces to give at the same time. All right, hell yeah. So let's give these things some values. We're going to say W is 250 newtons. And we have to use our equation that the force of friction, and I'm going to put a subscript max, is the coefficient. All right, ran out of juice. But force of friction mass is coefficient of static friction times that normal force. And so, and if I want to solve for the coefficient of static friction, I'm going to take the force of friction max divided by the normal force. All right, hell yeah. So I think I just confused myself. So let's just go back to a block, and I want to apply a load, and I know that it's going to be resisted by a force of friction. And max, that can be mu s times the normal force, which is mu s times the weight, because we have a weight here. And so, and I'm just going to put P max. This is a very good thing to do when it comes to material mechanics, because especially for anytime you have like a value that's max, just know that you can also put a 0 value and then any value between 0 and that maximum value. So that's but something probably special happens at that max value. Just using subscripts like that are good, because maybe you wanted to use half max and you're going to call that point, with the subscripts like design. You know what I mean? So there you go, P design. So we have a design load. So those subscripts are pretty good to use. And so again, we said that the force of friction is going to match whatever resisting force that you're pulling on those surfaces up to the point of mu Sn, and that's kind of the max value. So this, some of the forces, if we do a free body diagram on this mass, we have P max, and then we have mu S W. So those are the forces. And so when P max is equal to USW, or mu SW, the weight, a coefficient of static friction times the weight, that's going to be the load to get that block to move. And so, but on our new free body diagram, we are so instead of 1,000 newtons, let's let's treat this block. This is the block that we want to do a free body diagram on. We're going to have right here the frictional force, mu s, and sorry, this one's mu s. The prime was going to be the less weight one. So we got mu s, 2w. So mu s 2w is that max friction that can take. Up here, the max friction that this can take is mu s prime w. And then we want to know what P max that we can pull with. So there we go. So we have the force of friction max, and then the force of friction max prime. Force of friction prime max. So there you go. So now I'm satisfied with kind of looking at this thing, and we're going to sum the forces in the x direction, or 0. And again, this is going to be in equilibrium. The forces are going to be balanced, but if we put just one tiny bit more, a little bit of force extra, then we have movement. So that's the point of movement. All right, hell yeah. So we're just going to put negative, we'll do this one first, mu s 2w minus mu s prime w is equal to P max. Sorry, plus, so that those are the negative forces, plus P max is equal to 0. So P max would be equal to, we can factor out a w, but we're going to have w mu s, so 2 mu s plus mu s prime. So I just kind of rearranged the equation and factor. I probably shouldn't have factored. Probably made it confusing. But hell yeah. All right, hell yeah. And so bummer, because we didn't get anything that was very useful, or you know what I mean. And we actually have to kind of take a step back. But the reason why I simplified this block down to here is that when we apply this force, and this is kind of like, this mind melts me. Especially if one of these is like a rougher surface and then the other. Or, we have more normal force on this one and less normal force on this one. But the problem states that both of these we want to release at the same exact time. And so this is where I'm gonna and when we release these, I'm going to draw this in a, and I guess we'll have to get back to this one, but I'm going to draw this as this pole being kind of these round knobs, and then on this pole BC, and these are going to be the ends of the pole, and like an outdoor gate latch, they have kind of a mechanism like this, and then you have a spring. So let's say everything is frictionless. These rollers go up and down, but it requires a force this direction to pull it out. So as you pull this direction, you have to spread these springs, and those springs open, and then all of a sudden it slides out. And the cool about a demonstration like this, it's irrelevant of how much downward and upward force you put on these. And it doesn't really care. It will only open if you pull in this direction. And then so the reason why I wanted to make this block kind of small, and I could even make this a lot shorter, is that if I place a load here, and we're just gonna, let's just go back to that 1,000 newtons. This is going to get distributed half and half. And so from this point, we're going to have half is going to pop out of that socket and half is going to pop out of that socket. These sockets, or these kind of gate latches, is what the friction is doing. The friction is holding this system back. It's holding those molecules that are interacting, like stalactites, bending them, however you want to think about that, to a point where that force gets to be a max, and that's going to be, and it's going to pop that loose. And so this problem states that these both pop loose at the same exact time. And so if this force, and I guess what's complicated about this? Well, this force isn't in the center. And so if this force was all the way at point C and pulling at point C, point B wouldn't have any force really pulling on it, because all the load would be going through that pivot. So if you think of these forces of friction, these contact surfaces, as a gate latch that you can put load on until it pops, that's what's happening. Now this load has an X component and a Y component. And for the most part, and for this one, it's very useful to draw the Y component. You can draw these forces. The parallelogram method says the resultant force can be kind of broken up in horizontal and vertical components, and you can go two different ways. And you can use any two. I can use this vertical one and this horizontal one, and that's going to be useful because we have a component that's pulling up, kind of reducing the pressure at point C, because this gate latch, the value on it is that the strength of this spring on this gate latch is the coefficient of static friction times that normal force. That's going to be the number. That's going to be the max number to get that gate latch to pop. Same thing up here, and we're just going to have two different normal forces. Like the normal force right here is going to be hella heavy mass times G. The normal force at C is going to be this hella heavy mass plus the mass of this pole times G, but minus this Py component. So if this is bigger than that, and I think for this problem, I don't know which is big, but that's going to make the force at point C, let's say it makes the force, who cares? Let's say it makes the force at point C bigger. But now what? If I was pulling in the center, then this can take more force, so it has to be a less, you know what I mean? So this has to be a slipperier surface. If I have more normal force here and I want these to pop at the same time. But what we said is that if this force this Px is closer to C, like, hey, all of this force P, or this Px, is going to be trying to pop this spring, pop this gate latch. And hardly any is going to be popping that one. So since this is just kind of the feeling it out, I think it's good to get some numbers. I think we have enough juice to get some numbers at this point. And so we're going to show, and then this diagram was just to show you that I can have a different normal force up here than down there. I can have two surfaces, or I can have a chunk of something and pull it from the middle. And I can have two different forces on those surfaces. So that's just kind of the crux of this problem, is you're going to have two different normal forces. So let's explore what those are. And let's just use factors of 10 for this one. So I have 200 kilograms. That means that this mass is going to be 2,000 newtons. Okay, just 200 times 10, we got a weight of 2,000 newtons. The thing to look at is that this beam is supported on both ends, and then the weight is in the middle. So, do your free body diagrams, forces in the y, and I have two unknowns. I have to take moments about a point. And what's going to happen is that this is going to be mg divided by 2, and this is going to be mg divided by 2. But if I have a plank with heavy mass in the middle and two people have to hold this plank, each of them is going to have to hold half that weight. Cool. So we're going to have half the weight over here. And so that's going to be 1,000. So we have 1,000 newtons pushing down. The mass of this post is 20 kilograms times 10 for our gravity is going to be 200. So hey, so even right now, this point C has a potential to be 1,200 newtons, but we are pulling up with a 300 Newton force, and we have 3/5 of that going in that direction. When you get this, so this is the 3, 4, 5 triangle, and this is honestly where I really want to slow down and talk about, because we're using a triangle to break up a force. We're saying we're pulling in this direction, and then somehow we know that this component's going to be 3/5 P, and this component is going to be 4/5 P, just because a triangle of this same shape can have a value of 3, 4, and 5. And this side, all that's saying is that the length of this side compared to the length of the hypotenuse is 3/5. The length of this side compared to the hypotenuse is 3/5. So hell yeah, let's. This is the first time doing this, and I think this will be good, and to try to do this a lot and make other shorter videos. So it is going to be. We're going to explain why force vectors act and are kind of identical to right triangles. Like, why are those two things related at all? Alright, this is going to be so cool. So let's say you have someone's loading you up with books, and so the first thing that you're going to have is just one book, and that's just the weight of one book. We call it 1 Newton or whatever. Cool. So we have a weight of 1 Newton for that one book. Then we're gonna stack identical books. You're gonna carry identical books. So when you carry 2 books, how much is that gonna weigh? 2 newtons. Now I'm going to try to rattle your brain and say, why is that? Like, why isn't it? Why couldn't it be something different? And that's going to be very useful. I think there's a book called Einstein's Dreams. It's like a book of just pretending like you have smaller planets, where like this is the actual size of the people on the planet, but maybe it has gravity enough for them to actually stick. And then you just have all sorts of different scenarios going on. But you can, so I think it's very useful to be able to imagine that you can create your own universe. And every time you get a problem wrong, or do like like for me, I always make an assumption that's just awful, and then I don't know why I'm making that. And what you did is just you created your own universe where that assumption works, but that it's going to be contradictory to other things maybe. But hell yeah, so let's get back to this. So why not have a world where this first book weighs 1 Newton and the second book weighs 2 newtons minus 1, just a value of 1 divided by the 2 books in newtons. So we're going to have, so this thing is going to weigh 1.5 newtons. So yeah, it's going to be just kind of interesting. If you have 1 book, it weighs 1 newton. But if you put 2 books on, hey, it actually only weighs, 1.5. So hell yeah, let's stack the third book. So the third book is going to weigh 3 newtons minus 1/3 a newton. And that's going to be 2.66 newtons. All right, sweet. Let's stack the fourth book. And the fourth book is going to be 4 newtons minus 1/4 a newton. And that's going to be 3.75 newtons. And you can see that when we stacked the first book, we were just like, hell yeah, we understood that it weighed 1 newton. Something very peculiar happened when we stacked the second book. It just weighed half. The third book definitely weighed a little bit more. The fourth book is getting to be like weighing what we would expect. And even by the fourth, let's say fifth, and we'll do 10 books, 1, 2, 3, 4. So we got 10 books. That's going to be 10 newtons minus 1/10 a newton, just based on a formula I just made myself out of air. You know what I mean? And then so we have 9.9 newtons. So, I mean, this, if I stack 10 books, is very similar to what we thought. We get a little bit of a 0.1 newton break, but I don't know if we'd even be able to, 10 books is pretty heavy, let's say. And so it's going to weigh just slightly less based on, we're going to make up our own universe, and that's going to be what happens. All right, hell yeah. I bring this up because the concept of like stacking books that are identical, and you just being okay with the fact that if I have 2 books, it's like 2 times the weight of 1 book. And then 3x for the 3rd book, 10x for the 10th book. And so I just think we take that for granted. And so I think that's, I just thought that was useful, because when we talk about forces as at angles, and how they have, how it's very similar how they have components, how a force, you know what I mean, if you're, yeah, this is cool. I think this would be a very useful experiment to do. You know what I mean, especially for an engineering class, is to get rings where you can actually like hold on to them about like this, like, so pretty decent sized steel rings. And so I've been starting to do this with my problems, is like, hey, let's say I'm blindfolded, and so I'm holding on to this thing, and I just said that if I have, let's do with just a 30-degree angle force. So someone puts a force at that angle, and I'm just like, okay, I register that. And so it's going to be no different than if 2 students pick up these 2 strings. You know, this student lets go of his force, and then these 2 students apply the magnitude of force. So let's say this is going to be 10 newtons. This student, and this is 30 degrees, this student applies a force of 8.66 newtons, and this student applies a force of 5 newtons. I think this is a very better textbook example of like real world, is just like, hey, feel it, you know what I mean? And you don't even have to do this experiment. It's just like just like even talking through an experiment that could be done, be like, hell yeah, I could hold on to that ring. And the fact that these 2 students are pulling that amount, you will not be able to tell the difference between this 10 Newton force. And so I think that is pretty incredible. Alright, hell yeah. And so these values are nothing more than the length of this triangle. If I say this triangle is 10 meters, the length of this side would be 8.66 meters. The length of this side would be 5 meters. Now, newtons and meters aren't related. But the fact that this triangle, the force on this is proportional. So you can say they're proportional, and they're exactly proportional. If this, typically your force is always, your vector at some sort of angle, and can always be represented as your hypotenuse. And its components can always be and always are, well, can be represented as, I think some of the hardest problems are just like, hey, represent this force with these 2, with like something that's not 90. So this is going to be 10 newtons, and what is this going to be? That's where you actually just want graphically. You want to be like, hey, that's about 5, this looks about 6, and this looks about like 12. You know what I mean? So this 10 newtons can be graphically someone, and this is going to be your ring. This can be, if I have someone pulling at 10 newtons and I'm blindfolded and I'm hanging on, so I'm blindfolded, and hell yeah, and then this person lets go, but then 2 other students pull 6, and then 12 this direction. And that's the reason why you always want to do these, you always want to show the parallelogram, to get to here for this result. And I can go this way and that way, or I can go this way and that way. and those are going to be the same. And I can represent this as either this one and this one, or this one and this one, or this one and this one. Cool. So, but basically, if two students were to pull, they would have to pull this arrow and this arrow, and I would not be able to tell the difference. All right, sweet. So this is a subject that I swear I don't think people on the internet are tackling enough. And you know, I don't really watch too many math videos on the internet. But I mean, you see the ones. You know, things are, you know, anything with exponents and numbers, people just go crazy for. But actual, you know, like real basic knowledge that just gets glanced over, I think is the true gold. Where you're just like, whoa. Like, just this concept of just like, hey, sines and cosines, well, like, yeah, we get it. You know, we get how a force can be represented as two different components. But the reason, I mean, this doesn't even, I don't even tell you the reason why. It's just a fundamental property of the universe. I mean, you create a universe where it's different. You know what I mean? I think this I don't know. I just think this property is something that is it just is what it is. It's just something that we observe and probably hella take for granted. The fact that things at perpendiculars, they can be additive, but they are going in. Well, yeah, and then here, like, hey, these two forces aren't even perpendicular, but you still get to the same point, you know. So it follows its own recipe. You know what I mean? And we just, you know, because this is a 90-degree triangle, and so we're just money. This is our, if this was our hypotenuse. Hey, this would be our angle. And so this would be theta. This would be theta prime. And sure, we could call this sine prime theta and this cosine prime theta. And just have, you know, if you put this into your calculator, you would have to... one... You know, like, hey, this isn't 90, so whatever angle this is, like a 90 minus whatever, you know, some sort of angle. Yeah, you know, so I don't know where I'm going with this, but hell yeah, you could create your own, you know, different subscripts for sines and cosines based on triangles that aren't 90 degrees. There's nothing special. I mean, there's tons of special stuff about the 90-degree triangle, but you could still have a triangle that's, you know, where your triangle is always 30 degrees. So if this triangle is always 30, and then this is my resultant, and this is going to be 30, you know, that's the 30-degree triangle. This is theta. Hell yeah. This is going to be sine prime theta. This is going to be cosine prime theta. But these values, you're going to have to program in for this triangle. And this is good to continue on here, especially because some of these early chapter statics where you have to take like, here's your force, and you want to break it up into two components that are going in just random directions. And if this is 10, like, you might have to go out here 12, you know, 12 newtons. You have to go farther that way and then back 6. And so what that shows was that this was not a right triangle, it was 30 degrees. And if I have this 30 degrees and this is 10, just by even showing it like right here, if this is 10, this is bigger than 10. Let's say that's 12. And then this is this component. Well, if this is actually 30, this component is also visibly bigger. Yeah, so there you go. So if I drew this, a 30-degree angle here, and then came up and did a 10, and then put this at some sort of value of theta, just by observation, this almost looks like 14. Maybe this is 16. And we have a triangle where this would be your hypotenuse. your hypotenuse is this component. And here would be the angle relative to a 30-degree angle. So hell yeah. Alright, I know how to bring this home. So we tried our best. We did kind of a lousy job, but whatever. But we, and again, there is, just the magic is that, what is the magic? Oh yeah, that a force at an angle is going to have two components in the kind of orthogonal directions, the horizontal and vertical directions, that are proportional to the triangle that the angle of that force would make. So there you go. So if this was 30 and it was 10, this component is going to be 5 newtons. This component is going to be 8.6 newtons. If you made a triangle that size, and so let's make a triangle that's 5 meters. Well, this would be 2.5, and this would be 4.33 meters. And so so yeah, that's kind of interesting. How do we get this component? Well, we say 2/5, so the ratio of the length of this side compared to the hypotenuse, that's going to be 2.5 divided by 5. It's not 2/5, but 2.5 divided by 5, that's a ratio of 1/2. Therefore, the force component on this side is going to be 1/2 times 10 newtons. Alright, so here is going to be 4.33 divided by 5 as a ratio. Let's multiply both top and bottom, get the denominator as a function of 10, then we can just move the decimal place, and this is going to be 8.66. Let's move the decimal place 1 to the left, and this is going to be 0.866 times 10 newtons. So that's going to be the fraction of 10 newtons, and we're going to get 8.66 newtons for that side. So sweet. I don't know. I just really felt the need this week to start making videos on that topic. Now, for our problem, I said that it's going to be very similar to gate levers, and yes and no. Gate levers, and I said gate levers, it would be irrelevant whether the force would be down and up on a gate lever. So now we actually have to, the actual scenario that's going on here would be, these things resting on a spring. Yeah. Let's do this. I think I got this. So we're gonna have this right here, and we're gonna have this at this height. So here is our catches, and it's free to just pop out. We're gonna have a spring right here, and then this is gonna go around like normal. Hell yeah, cool. And so this is that's that one, and we're gonna draw this other one. So I think it's just very good to like visually come up with a scenario that you could play along with, or actually make. Like, you could make this scenario. It would just take a lot of time and effort. So what happens is that we're just saying there's a connection between when this spring goes down, this spring closes. So if I put a lot of force, a lot of weight down on this spring right here, that this spring expands, and then that these close, making the force to pull this thing out harder. So that is a better representation of what's going on at point B and C. And we can still pull our force directly in the middle. So we're going to pull with the force of 1,000 newtons. And a free body diagram of this thing. And let's try to do the whole problem. You know what I mean? So we have this post. We know we're going to have 1,000 newtons on it. Yeah, so let's actually try to do this problem. our P is going to be 300 newtons. We have two components, a Py, which is 3/5. So 3/5 of 300. See how I do this kind of fast? Is get your denominator to be a function of 10. I'm going to multiply top and bottom by 2. And this is going to be 6/10 times 300. And so this 10 just means I can move this decimal place 1. So we have 6 times 30. 6 times 3 is 18. Times the extra 0 is 180. So yeah, so we have 180 newtons there. This one's going to be 4/5. Let's try to do that same thing in our head. I don't want to do 4/5. Anytime you get a 3/4 triangle, also make it a 6, 8, 10, because now I'm going to have 8 divided by 10. So that's going to be the ratio. I'm going to do 8 divided by 10 times 300, which is same thing as 8 times 30. 8 times 3 is 24. 8 times 30 is 240. Booyah. So we have 240 newtons right here. Okay, we have a weight of this pole, which is going to be 20 times 10. That's going to be another 200 newtons. And then we're going to have our force at C. I'm not even going to label these. I'm just going to say, hey, let's just figure what is it? So we have 1,000. Or let's do this. We have 200 down and then 180 up. That's going to be a resultant right there of 20 newtons down. We have 1,000 newtons down, so we're going to have 1,020 newtons up, and that's going to balance in the y direction. Alright, hell yeah. So these two things are just more fictitious. They don't fit into the free body diagram analysis. But what I'm saying is that this is the load on this spring right there, and then this is the load on that spring. And so, this is the normal force associated with the frictional force. We said the force of friction was the coefficient of static friction. This is going to be at point C, times the normal force at point C. So that's the normal force at point C. Up here, the force of friction is mu s b times the normal component at B. And so that's what we have for the normal component. Alright, hell yeah. So now what we're going to do is just try to simplify this, because we said that this horizontal force, it is actually 0.75 meters from here and 1 meter there. We're just going to say it's dead center. And if that is dead center, this force of 240, that horizontal component, has to be balanced by these two forces evenly. And so we're going to have a 120 newton there and a 120 newton there. And then that'll finish our equations, because right here we said the force of friction, that's going to be the 120 newtons, is equal to mu s, this is going to be mu sc, times the normal force of 1,020 newtons. And we can just solve for mu sc. Up here, we're going to have 120 newtons is equal to, that's going to be the force. This is going to be the force we need to overcome to get this thing to pop. And so that's mu sb times the normal force at B, which is 1,000 newtons. And then we can just solve for that. You know what I mean? We're just going to have 120 divided by 1,000. This is going to be 120 divided by 1,020. Now that's the ideal scenario. The only thing tricky with this is that this horizontal component is closer to C. And so a lot more of this force is getting ripped out at C, and so that means that the coefficient of friction at C must be bigger than B. I mean, the normal force is already bigger at C. So the upward force was only 180. The downward force due to this pole was 200. So from this problem, the normal force at C is bigger than B. And then I'm going to, and what is our answers? I'm going to pull that up. Alright, so we're going to do our kind of just first check on reality. What did we say? We said that we're going to have All right, I got some more juice. And so yeah, let's talk our way through this. This is the answers, but still, like nothing's popping right now. So the normal force at C is going to be bigger, which would indicate that the coefficient of friction at C has to be less. You know, okay, so we got two things going on, but the force being pulled at P, the component of it is way bigger. And so if these things are going to snap at the same time, then this has to be bigger as well. So two things are making this bigger. So I was wondering if we were going to get a contradiction. Or just two things where one is going to make this value go up and the other is going to go down. But both of those scenarios make this value go up. If I want to pull dead center and this has more weight, I need to make that is different. So if I want to pull dead center and this has more weight on it, I need this coefficient of friction to be smaller. I need this to be slipperier because it already has more weight on it. But the difference between the weight is very negligible. It's just 20 newtons. Cool. The next thing, though, is where we're actually pulling. If I'm pulling right at point C, point B isn't being pulled at all. I can pull an infinite amount, force at point C, and point B is not going to feel anything. If you're kind of treating these as, even though these are just frictionless surfaces, you can still kind of treat them like rounded, almost like joints, where you have bearing joints. And it's the same because what you like, and you kind of have a sideways bridge. If we look at this bridge sideways, hey, we have the frictional forces are what's holding it up, and then we're putting a downward load, in the middle, P. And so that's the same thing as having a bridge with the load P in the middle, and then you're going to have P divided by 2 on both sides. Now, if I move this load to one side, then this side just becomes P, and this side doesn't have to do anything. The support on that side doesn't have to do anything, and that's if weight is negligible. If you just have a chunk of foam, and then you're just resting it on kind of a flat surface, and you have, and then you literally, stand over here. Hey, I bet you a little gap raises over there, just from the compression or something. So, but you won't have any force if this is just a chunk of foam. All right, hell yeah. And so that is moving this force closer to that point. So if I move this force closer to here, then all that force, the horizontal components, being resisted by this friction. And I have no chance for that to even pop. But we're not putting this force all the way at point C, this horizontal component. We're just moving it just slightly. But even just moving it slightly means that more force is being pulled at C. And if that's the case and I want these to pop at the same time, this has to be bigger to keep resisting until this gets enough juice to pop as well. Alright, and since this is just the intro, we're kind of just going over the things that feed this problem. Well, let's go there in a second. What we're going to do is show that if I have two supports and I put the load in the middle, P, that these are P divided by 2, P divided by 2. Now this is an equation. Like this is a distance, let's say this is a distance of 1 and 1, and this is a distance of 2. That can be useful. Or you could say it's a distance, I guess two different ways to look. You could say this is a distance of a half, and this is a distance of 1. And if this is P divided by 2, P divided by 2. So let's try one. Let's say this is a distance, and I'm gonna try my method. This is a distance of 1, 1, and 1, and this is a total distance of 3, and I want to know the loads. Now what you would do is you would sum the moments here and see that this load is a distance of 1, and this load is a distance of 3, and those moments are going to counteract. So let's do that. So we're going to have negative p times 1, and then we're going to have plus an unknown times a distance of 3 is equal to 0. So that's the sum of the moments about this point. This is going to be p is equal to, it's going to be 1/3 p is equal to that unknown. So this is going to be 1/3 p. And then if I do sum of the forces, this is going to be 2/3 p. And so what we have is, I have, this segmented up into 3 segments. And let's do it like this and see if this is going to be 1/3, this is going to be 2/3. We have p. And then we want to figure out what these are. Well, this value is going to go right here, 2/3 p, and then this value is going to go right there, 1/3 p. I think it can be kind of hard to memorize this one. That's why you'd always want to do some of the moments. But let's do one more. Let's say we have something broken up into fifths, and I'm going to put the load. I'm going to put the load right here. So I'm going to put a load P right there. These are 1 foot each, so we have 5 feet. This is going to be 2 feet. This is going to be 3 feet. And I want to know these loads. Well, one is just to start with the ratios. Like, hey, this distance is going to be 2 fifths of the entire length. And then write both ratios. This length is going to be 3 fifths of the entire length. And these ratios, the distance between the total, are going to represent the forces. So we're going to have a 2/5 p and a 3/5 p. And then just by inspection, you want to say, like, hey, if the force is getting close to here, this is going to be the bigger number. And so this one is going to be 3/5 p, and this is going to be the smaller number, 2/5 p. And so, sure, these like this 3 is opposite of that, this 2 is opposite of that 2. But I think that's kind of going to be my method going forward, and it is very good to memorize this one. Like there's some JEE problems where if you don't just have that on lockdown, like one was one was in force. So you had 1, 2, 3, 4, and then you had something. No, I think I forget what it was. It was almost in tenths. All right, I'm just gonna move on from there. But hell yeah, so that's find the ratios, and so that's where like doing this problem, I think it can be very useful to start doing problems with fractions. So this 1/5 just becomes 3/2. Same thing here, 3/2. This one is still 1, and this is 3/4. So now we have a total distance of 1 plus 3/4. This is going to be 4/4. Multiply top and bottom. Turn it into a ratio. Multiply top and bottom by 4. And we got 4/4 plus 3/4. This is going to be 7/4. So this total distance is 7/4. And so now I can do my ratios. One ratio is going to be 1 divided by 7/4. Which is a ratio of 4/7. The other ratio is going to be 3/4, this length, divided by that total length of 7/4. Same thing as multiplying by the reciprocal. 4's cancel, and I get 3/7. So even just right here, I have something that's leveraged in the middle. I'm going to identify it very simply as like a beam where this is distance A, this is distance B, and this is length. My two ratios are A over L, B over L. One is going to be bigger, and so that bigger value is going to be associated where the force is closer. So there you go. So if this is P, this is going to be B divided by LP, and then this one is going to be A divided by LP. And so our ratios are 3/7 and 4/7. And with your ratios, just always make sure to add them together. 4/7 plus 3/7 should equal 7/7, and that should be your total. Oh, hell. Did I mess up? This total length is 7/4. So I feel like I might have messed up. What's the other ratio? We got 4/7 and 3/7. No, I guess that's just a percentage of the whole. Is that gonna work out? All right, sweet. Hell yeah. So the take home is that these two ratios have to add up to like 100%. Anytime I'm working with fractions, I think of like percentages. The human mind, I think, works in percentages way better. But we have 4/7 plus 3/7 is 7/7, and that's a total of 1. And so we're back to 100%. So we do have, yeah. So we're set there. But let's do the comparison, because over here we have the ratio of A divided by L plus B divided by L. That's going to be A plus B divided by L. A plus B is L, and we have L divided by L, and that is a ratio of 1. So we have that kind of 100%. And because the sum of the forces in the y direction have to equal P, is that this component plus this component have to equal P. And so if we take both of these values, so I think it's better said to be like B divided by L times P plus A divided by L times P has to equal P, and that's what we find, because we have A plus B divided by L times P is equal to P, and then this is L divided by L times P. And so we have a check on reality there. But I'm going to do one more double. I said this was the total length, and I had a ratio of 1 divided by 7/4, and then also a ratio of 3/4 divided by 7/4. And if I added these up, I should get the total length, which is 7/4. So let's do that. So this 1 could be considered 4 divided by 4, 7/4. Plus 3/4 7/4, you know what I mean? And then we have denominators are the same, and so we can say this is 7/4. Oh, yeah, I guess these still are ratios. These are going to be ratios more related to percent, but this top value I can get to look like the total length divided by yep. So I think I was thinking something different on that. I'll try to think about it for a sec. Alright, hell yeah. So never mind. No, it's like you have these two values, and both these would add up to that total length. You're taking this divided by the total length, and that's going to be a ratio. You're taking this divided by that total length. That's another ratio. You add those ratios up, you get 1. You don't get the total length. I mean, you're already saying, yeah, it's very similar to saying like, hey, if this is my hypotenuse and this is my opposite, is that opposite divided by hypotenuse is the fraction. And that's why I like to think of this. If you always do this by 100%, that is the percentage of this side compared to the hypotenuse. And so that's what we did here. We took this component, like let's say it's this side, and we compared it to the total length. So that's like taking this compared to the hypotenuse. And this is a great example, because if I take this adjacent compared to the hypotenuse, I'm going to get a percentage. But these two percentages do not add up to 100%. 0.5 plus 0.866, or 50% plus 86.6%, hell no, do not add up to 100%. But very interestingly, with the right triangle, if I square those percentages or fractions, for sure we get 0.25 plus 0.75, and that does equal 1 or 100%. Where here, we're doing something more rudimentary. We're taking this component divided by this total length, and that basically is a percentage of this length compared to the length total. And then we're going to take this length and divide it by length total. That's the percentage of this. I mean, it's similar. If you took this length of 0.75 divided by 1.75 and then multiplied by 100%, that's the percent of this length compared to the total length. And then the other equation would be 1 meter divided by 1.75 meters. That's this total length times 100%, and that's going to be the percent of this length compared to the total length. Add those two percentages up and you're going to get 100%. Booyah. Alright, hell yeah. And so now we're just kind of, practicing whatever we want. So let's try to do a speed run where we just say, hey, this is yeah, let's do a speed run just using the values that we said. This was 200 times 10. This is going to be a weight of 2,000 newtons. I'm going to have half of it's over here. That means half of it is pushing down on this post, so we have 1,000 newtons down. The post itself at the halfway point is going to be 20 times 10. That's 200 newtons. This thing has an upward component, so we have Py is going to be 3/5, which we said is better represented as 3/10 times 300 newtons. Okay, sweet. So that's going to be 6 times 30. 6 times 3 is 18, 180 newtons. So we have 180 newtons up. And then we have this component, the horizontal, is going to be 4/5, better represented as 8/10 times 300. That's the same thing as getting rid of a 0. 8 times 30, don't know it, but 8 times 3 is 24. Booyah, we got 240 newtons. And so we got 240 newtons that way. Okay, hell yeah. And so then the sum of the forces in the y, we've done that one before. We have 200 down, 180 up. That's going to be a resultant of 20 down, plus the 1,000. So we have to balance it here. That's going to be 1,020 newtons up. Now we do have this force that's 240 newtons in this direction, and we know more of it's going to be over here. Our two ratios are going to be 0.75 divided by 1.75. And it's good to get starting to do these as fractions. This is going to be 7 fourths. 3 fourths divided by 7 fourths. Hey, the fourths cancel. I can do that one visually. This is 3/7. Now the other ratio should be, since we already went over it, 4/7, because those two ratios should add up to 1, but let's do it. The other ratio is going to be 1 divided by 1.75, which is 1 divided by 7 fourths, just the reciprocal of that. So booyah. So we have our two ratios. This is going to be the bigger ratio. My force in this horizontal direction is closer to point C. Therefore, this component, this point is going to see a bigger load. Like basically, if I had to, So, like, the arrows that I just drew are the resisting forces. So let me draw those in very carefully. That's going to be mu c times 1,200 newtons. This up here, this resisting force is mu b times 1,000 newtons. Still just using kind of intuition of what we know about frictional forces. The resisting frictional force is the normal force times that coefficient of friction. Booyah and hell yeah. So now we're on a roll. But those are the resisting forces. What we did here with this ratio is we basically it's like, hey, what if I moved? I think it's the same thing as like moving this 240. Like I know I have this 240 in the y, but it's got to be similar to splitting it, a portion of it here and a portion of it there. And so we said, so I'm just going to like kind of cross this out and say, hey, it's almost like we're putting this force right there and there, but this one's going to be at that bigger ratio, 4/7 times 240 newtons. And this one's going to be 3/7 times 240 newtons. Okay, so that is the full free body diagram. This load is basically like saying it's going to be pulling there and there. And so that's kind of out of the question. But we have to resist it by those two. And so now we're just down to the grit. And we can just solve, like these two are going to pop at the same time. And so, and these are the loads that are going to, we're applying that 300 newtons. These are going to be the loads. And so for this, and these are the resisting forces. And so we're going to say this load, if I added just a little bit more load, it's going to pop that resisting force. Here, if I just add just a tiny bit more load, it's going to pop that resistant force. So this is the load that, you know, and that load is this. That is the pulling force at that joint that is causing that to you know, this is force of friction max, mu n. Hell yeah. Okay, so we have two equations. We have 3/7 240 is equal to mu b. And I'm just going to get rid of the newtons, so they're on both sides, and this is a ratio. So, and then this is a unitless, so hell yeah. So then we have 1,000. So that's mu b. And then we have 4/7 240 is equal to mu c, and we do have 1,020 here. So let's solve for mu b. That's going to be, and this is going to be, let's do 3 times this. That's going to be 6. That's going to be 600 times 120. That's going to be 720 divided by 7, and then divided by 1,000. All right, sweet. And this is where I was able to guess. You know what I mean? Because we have, anytime you have a 7 down here, well, oh, never mind. Well, I mean, I could just cancel those 7s, and it's like we have 1 and a 1, and then just move this decimal place 3 locations, and we're very equivalent to 0.120. So that should be pretty close to what that is. And where's our answers? Hell yeah. And so mu b is, oh, did I mess up? Ooh, we better just check our answers with our calculators. So we have 3 divided by 7 times 240 divided by 1,000, and we get, so I was off by a decimal. Oh yeah, because no, well, yeah, I don't know why I was off by a decimal on that, but this is going to be 0.10287 whatever. This mu c is going to be 4/7 times 240 divided by 1,020. And this is going to be 0.13445. Hell yeah. So that was using a G of 10. And so we're a little bit off. You know what I mean? This is 1.13, and this is 1.028. And so let's now kind of slow it down, and we're going to use a G of 9.81. And then this is going to go to 1.04, and this is going to go to 1.37. And that's going to round to 1.4. So these are just kind of the two answers that were given in class of representing the answers. You know, even though they don't have significant figures, no one's really paying attention to those on that one. All right, so hell yeah. So let's do this kind of start to finish. All right, booyah. And we'll try to do free body diagrams. So we're going to take this plank AB, and we're going to have a AY and an AX. And then we're going to have a BX and a BY. Alright, sweet. And then we're going to have a load right in the middle. And that load is going to be 200 times 9.81. Sweet. We know that this is going to be half that. I mean, yeah, so let's not do the sum of the moments. I mean, we could sum the moments at A, might as well. Sum of the moments at A are 0. So this distance is 1.5 meters. So we're going to have a negative 1.5 meters times this force, which is 200. And this is 200 kilograms, and this is meters per second squared. 1 kilogram times 1 meter per second squared is 1 newton. So that's where that comes from. So we have 200 times 9.81. And then we have a resisting force of By. So we have a positive moment from point A. It's a distance of 3 meters, and we have By as our force. Since we took the moments about A, these forces go through A, and then Bx goes through A. So those are the only two forces that are causing this thing to have a torque about point A. And those are going to be balanced. So we have By, let's get this to the other side, and then divide by 3. 1.5 divided by 3, the meters cancel, and we get 1/2. So we get 1/2, 200 times 9.81. I'm just going to say this is 100 times 9.81. And that's newtons. Or no, we can just say 981 newtons. All right, so now we know what By is. And cool, and we have it drawn. Now with the equal and opposite thing is that is going to be holding up this plank, but that means that there's an equal and opposite By on the plank below it. That's all I'm going to say about that. I think that's the hardest thing to... Alright, we ran out of juice, but yeah, equal and opposite is difficult. Anyway, so this post has a weight of 20 times 9.8. So we're gonna do that. The weight of the post is 20 times 9.8. This is going to be similar to 2 times 10 times 9.8. 10 times 9.8 is going to be 2 times 98. So hell yeah. This is very similar to, and we could have just got there, right? 20 times 10 is about 200. 2 times 98 is going to be very close to 200, but minus 4. So we got 196. So sweet. So we have 196 newtons down. At this point, which is 0.75 meters, and this is 1 meter, we're going to have a horizontal component, and that was going to be 4/5 times 300. Sweet, that's going to be 8 times 30, which is 240. So we have 240 newtons. The y direction of this was 3/5 times 300. That's going to be 6/10. So that's going to be... Alright, hell yeah. Sorry about that. We're just running out of juice. But yeah, 3/5 is 6/10, and that's going to be 6 times 30, 180, because 6 times 3 is 18. So we have 180. So we have 180 newtons up. And then we have our, and this By was what? 981 newtons down. And then so I'm going to put in Cy, and that's going to be the sum of the forces in the y. So I guess we can do that. Sum of the forces in the y are 0. We got negative 981 minus 196 plus 180 plus Cy is equal to 0. So get these to the other side. Those are going to be positive minus 180. Look at this. This is just going to be 16 So we're going to, after we do negative 196 plus 180, we're going to have negative 16. So that's going to be, CY is going to be adding these. We're going to have negative 799. So there you go. So CY is 997 newtons. Booyah. Okay, so we have this force, and we need to balance it with CX. So CX, and we're going to balance it with BX. So these, and these are the frictional forces. What's balancing is the connection of friction. You know what I mean? You could theoretically say, hey, this post, like there's nothing touching it except those connections of friction. And those are the things that are resisting. And so those are going to be, if we have this 240, those two have to equal those frictional forces. And now we have to use the sum of the moments about one of these points to find the other. So let's do sum of the moments about B. And all of these forces in the whole vertical direction go through B. So does BX. So the only two forces we have is 240 and CX, and they're these distances away. So we have right-hand rule for this one. That's going to be 1 meter. So we have positive 1 meter, 240 newtons, minus 1.75 meters times CX is equal to 0. So CX, let's just get it to the other side, is equal to it's going to be a ratio of 1 divided by 1.75 times 240 newtons. So that's CX. And let's do that. 240 divided by 1.75. It's not a nice number, but we get CX is 137 we'll go 5 decimal places. Cool. There you go. So there's CX. The ones in question are the vertical forces. So we have B, Y, and CY. And we have CX. And now we just needed to sum the forces in the X direction is 0. So we have BX. So we have a negative BX plus 240 newtons. Minus this, so minus 137.14. I'm going to store that as alpha C. And this is equal to 0, so let's get BX to the other side. We're going to have 240 minus that, so BX is going to be 102.86 newtons. I just rounded to 5. Alright, perfect. So now we can put it together, because these frictional forces, what did we say? The frictional force max at point C would be mu C times the normal force. And see, this is where we don't want to get, again, draw. I don't know, I'm probably like missing a step here, but I want to apply a load P. And at point C, it's going to be, hey, I want this to apply the load CX. Because that's what this load has to see, CX. And I'm just going to apply it in this direction. And so I have to resist this load, but just barely. And that's going to be mu C times CY, the normal. You know what I mean? So we have mu normal. And then this would be the force. Anyway, so those are the forces that are balanced. And so, yeah, so we just have CX is equal to mu C CY. If I want to solve for the coefficient of friction at point C, it's going to be CX divided by CY. It's going to be the horizontal component divided by the normal component. And so mu C is going to be CX divided by CY, and it's going to be this divided by that. So we have alpha C divided by 997, and we get 0.1375. Hell yeah. And then the other one would be mu b is going to be, bx divided by by. It's kind of same equation, just switch the c for a b. And we get mu b is equal to, alright, bx was 102. Let's store that as alpha b, divided by 981. And we get, what? Oh, yeah, let's do this again. Alpha C is this, so 240 minus that is this. I'm going to store that as alpha B. Sorry, I was just off by a factor of 100. I don't know why, a factor of 1,000. Alright, so we have bx divided by 981, and we get 0.1048. And hell yeah. Alright, and so those were the answers, and we did it. And we talked about a lot of theory going into this one, how to visualize maybe what these frictional, components could be. How you have this is a long post, but it's still just like a block. We did some analogies here. The only one that that we should have played around with was this one. And then just varying the location of P. So let's say P is down here, and then here's still the stiff springs. And then here is the loose springs. And then I'm pulling P. Well, more of this load is going to go into here, and let's say this is 1/5 and this is 4/5, the distance. So those are the ratios, and we have a distance of 5, and these are, so the load here would be 4/5 P. The load here would only see a 1/5 P. And just to make these pulleys fixed. So if I pull on this is, that's when this force is more centered over that location than over that location. Alright, hell yeah. So I think I'm done with this video. That was a long one, you know what I mean? But I'm pretty satisfied. Pretty satisfied with this one. So thanks for joining me. And that's a video.